All right, thank you guys. All right, so we already talked about the company briefly, and that's not the point of this presentation anyway. Let's jump right here. We're talking about high performance computing at the edge. A little bit of a dovetail from the previous presentation. Everybody in this room already knows what edge computing is, but I wanted to just set a baseline so we could all be under the same, starting point anyway from a perspective view. Broadly defined, edge computing is anything other than data center type computing, whether that be on-premise or cloud-based computing. I don't think I'm telling anybody in the room something new with that statement. But where I do want to start is how important perspective is. When we hear all these words in the industry, edge computing, high performance computing, heterogeneous computing at the edge, AI at the edge, edge is getting used a lot. But perspective is incredibly important to our customers, our end customers when we start talking about the edge. And what I mean by that is if you are a battle space commander of some type or another, whether you are at the Pentagon, at a base, at some deployed operating position, if you are operating in an environment like the big picture there, everything else to you is the edge. A whole F-35 is an edge. It's just an edge sensor flying out. I mean, F-35 is a very advanced sensor, but in a sense, it's an edge sensor giving data back to you. That is a perspective of a decision maker in that room. And satellites, ground vehicles, marine vehicles, helicopters are all sort of coming at it from the same perspective. They're all edge sensors providing information back. But there's a different perspective, and I think it's perspective that this room cares about a lot more, which is all right. That's one perspective, that type of concept of what the edge is. But then there's the actual platform perspective. When someone, maybe your customers, maybe a partner, is talking about pushing to the edge, pushing to the edge, pushing to the edge, what do they really mean when they're talking about pushing to the edge, and where is it a good idea or not? If you're working on an F-35, for example, and this is a public distribution, publicly marked document, you can see an edge concept here is there's all sorts of sensors. How far to the edge do you push that processing? How close to the aperture can you get that processing? And what are the benefits of not pushing all the way to the aperture if that's the edge that you want to define? And that's really the point of our topic and what the industry is doing there. And I have the F-35 up here, but I want to stress it is not unique to the F-35. I don't care if you want to talk about future vertical lift or XM30 or NGAD. They all have this same dynamic going on. And I did note on here, and I do want to do, so do the legacy platforms. You're upgrading F-18, F-16, Stryker. They have this same trade-off going on too. So it's not just anything that's relatively new. When you talk about push to the edge and you look at the sensor suite, there's a natural inclination to say, go closer to the sensor, go closer to the sensor, go closer to the sensor, right? And there's good reason for that. As they produce more and more and more data, which was just discussed, there are some benefits of getting that processing closer and closer to the sensor. But it's a trade-off, and it's a difficult one, and I want to highlight that. It is not a given that you should just push processing closer to the edge. And why is that? There's some real-world geometries that sometimes we fail to talk about a lot when we talk about pushing to the edge. Radar warning receiver, or a distributed aperture sensor, right? A DAS is an easy one to take. It's basically a video camera pointed in multiple directions, right? Well, pushing closer and closer to the sensor doesn't really solve the problem, because any modern DAS system is going to have 3, 4, 5, 6, 8 different cameras on the aircraft. Pushing closer and closer to the aperture of one given camera doesn't solve the problem, right? It doesn't, in fact, maybe make it worse. So pushing to the edge, as you hear so oftenly said, maybe isn't exactly what our customers mean when they say push to the edge. Further, there's the multi-domain aspect. Maybe you can push to the edge of a radar, but the radar is only one domain on any modern platform. It isn't your EO, generally speaking anyway. Sometimes it could be your RF. There's a lot of push in the industry to go to multifunction apertures, and we think that is a great thing to happen. It's going to happen, I would put it that way. Still doesn't solve the geometry problem. It still doesn't say that I can put one sensor on the aircraft and put all my compute right in that aperture as close as possible and solve the problem. The other problem with pushing and pushing and pushing to the aperture is you have pretty much cut yourself off from any dynamic computing trade-offs, meaning put in a GPU, put in a CPU, put in an FPGA, put in an AI edge processor. Well, if I push them all to the aperture, and it only is tied to that aperture, I've pretty much lost my dynamic capability to say, well, at one moment, I want to use those processing resources for this mission, this application, but in the next moment, I want to use them for this mission, this application, this data set. If you push to the aperture, you kind of cut yourself off from being able to make those dynamic trades. Further, and probably really importantly, I know there's a lot of buzz about AI, ML, and I think some of it is hype, frankly, but I think a lot of it is real and will become real. If you make decisions today, and this is something that real system architects are trading and wrestling with today, if you make decisions today to push the processing as close to the aperture as you can, you're essentially cutting out data. That is the nature of processing at the edge, right? You have to do some down converting, you have to do some data sampling, and you're effectively taking data out of a future centralized sensor fusion processor that might run future AI algorithms, ML algorithms that could have really used that data, and that data is not there anymore, and you can't get it back. It's gone, right? So our architects, generally speaking, the people that are all our customers in the room, right? Our system architects, they're struggling with this today. They need to build systems that are going to process data today and run algorithms and unknown missions and unknown AI processes of the future, right? They have to make decisions today without even knowing what the AI algorithm is for tomorrow. And I talked about the heterogeneous processing elements and that dynamic. That's another part of it, right? They only have so much size, weight, power. It was just talked about. Well, they have to decide, how am I going to place and use that size, weight, and power in a fashion that is as dynamic as possible? So when I want to run something else tomorrow, I can do it. And that's where this might be a little bit counterintuitive, maybe not. Maybe everybody in the room is already saying the same thing, which is it's really not a push to the edge when you look at it from a platform perspective. That's not what's happening in the industry, is at least our proposition. It's really a pull from the edge. You don't want to process up in the aperture. You don't want to do any processing in the sensor if you can help it. And I know there's going to be some people who say that's not possible, and that might be today. But if you look at what the model really needs to be, is you digitize in the center aperture. And hopefully you get these multifunction apertures that take care of a huge spectrum. But basically, I would propose you want to digitize at the sensor and then use very big pipes to send all that data to a centralized sensor fusion processor that has all these dynamic elements for processing that you can allocate in any given mission, any given function, and you can then use your big data sets, AI, ML, algorithm processing across all this disparate multifunction data. That allows the dynamic allocation of processing elements, sharing of data, not just across geometrically separated sensors, but domain separated too, EO, RF, EW, et cetera. It also does one thing that isn't technical at all in nature, but it is something that gets talked about quite a bit. It decouples your sensor from your processing hardware, and then even further, your processing hardware from your algorithm vendors. If you think about that, not from a technical perspective for a second, but from a market dynamic perspective, it would do a lot. You can purchase a sensor from the world's best sensor vendors. You can purchase processing hardware from the world's best processing hardware, a dynamic market. And you can purchase algorithms, software capability from people that don't build either of these two things. That doesn't happen today. And if you hear our customers talk, that's the world that they want to live in. Lastly, and I talked about a bit, this model would allow you to have a future where you don't know the algorithms, missions, and functions you want to run and have your best shot at being able to run them over the whole data set. So here is where I hand it off to Ryan, and he's going to tell us how we're going to get to this possible world.
All right, so if we want to have this, this architecture where we have access to all the sensor data so we can do sensor fusion and new AI, ML algorithms, there's a few things that we think that we need to make this happen. So first, we need high bandwidth optical interfaces so we can move all this data, from the external edges of the platform to this, heterogeneous compute in the middle of the platform. Second, we need swap optimized RF and optics on the edge to make this happen. And then we need rugged, heterogeneous, dynamic computing infrastructure in the center. So what do we have available to make this happen? We think there's a key enabling technology out there as far as multi-chip modules and multi-chip packaging. So you've seen capabilities, in a previous presentation, there was a whole supercomputer taking up a whole room at a system level. That's moving down to the board level, and then these technologies that used to be separate components at the board level are now becoming chiplets and single pieces of silicon in a single package, and they're really shrinking down the area, shrinking down the power, and we think this is a key enabling technology to be able to make this happen. Two of the big ones that are available today are RF, A to D, D to A. That stuff is being brought in package with some of the DSP processing. And you see that already today with AMD, Xilinx has their RF SoC, Intel has their direct RF parts now. So they're already making this happen with the A to D, D to A rate and chip. The next big one we see coming is optics, so integrated photonics in package as well. A lot of work is being done in that field. And there's chiplets and prototypes available where you can put the optics directly in a package and have optical fiber coming out of those packages. And they're seeing huge improvements in bandwidth, huge decrease in power per bit that you're moving. And you're also reducing the complexity on the board as well. So these two technologies we see are key to enabling this to happen. So at the sensor, you're really digitizing that data and then moving it over an optical pipe back to some central processing location. And this chiplet technology isn't just limited to RF and to optics as well. We're seeing best-in-class silicon, whether that be CPUs, GPUs, FPGAs, moving to this SoC infrastructure. And in the future, it's not just going to be a single company doing their own chiplet integration, but we see a world where you can go get the best GPU and combine that with a CPU and a GPU and memory, RF, optics, all in a single chip. So you're doing what used to be done, on a board with multiple plug-in cards. That functionality is going to go to the chip, and that's going to reduce power, that's going to reduce area, and significantly to reduce board development complexity as well. Now you envision, what used to be done on a board with multiple chips. You have a single package with coax cables coming out of it, optical cables coming out of it, and that's kind of like a little board in a package in itself, and you're just applying power, ground, and maybe some low rate GPIO to this thing. So this whole chiplet infrastructure we think is going to dramatically change what we can do in these rugged computing environments. So it's easy to throw a bunch of processors and computing elements into a package and think you have a problem solved, but one of the things that happens is you have significantly complex interconnects that need to be solved now. So you have heterogeneous computing elements that need to talk, they need to share memory. How do you get this done? Well, there's some interconnects that need to be figured out. It's not just enough to have 100 gig pipes connected back and forth between things. So there's new protocols that are being developed to help these things. Rocky V2 is one that exists today. If you look at a VPX chassis and you have a GPU card and a CPU card, and you want to get data into that, you can do RDMA over converged Ethernet and get that data into memory for those processing elements, and do that with limited impact on the compute. So you can spend all your compute cycles doing your workload rather than trying to move data in and out. Another one that's coming that's available is CXL. And this is a cache coherent interface, so now you have the ability to share memory resources across multiple processing elements and share that data in a much more simplistic way to the user. And as we move into this world of chiplets, that same technology is being pushed down into what's called the universal chiplet interconnect. And it's going to use some of these things from CXL and PCIe and allow you to have multi-vendor silicon in the chips. So from a standards perspective, we think the standards have done a great job evolving over time so that we can take the best-in-class commercial technology and put that in a rugged form factor that we can deliver at the edge. And we think that VITA continues to push the envelope here. There's great work being done in next-gen VPX and with some of the small form factor VNX, but just continuing to allow you to utilize the technology that's coming is extremely important. So to close, we just wanted to provide one example of where this is being done today. This is a 3U VPX module that actually has Samtec Fireflies on it, so 700 gigabit per second of optical I/O interface, going to an AMD SoC, which has a large FPGA fabric, specialized AI processors, CPU resources as well. And it's able to take in a large amount of data and do AI processing on this data. So this is a real-world example of this architecture being implemented. And based on our customer needs, we see in the near future that they're going to need to support 5 to 10 times the amount of bandwidth that this module does here. So with that, I will open it up to questions.